Okay, we are looking at Chapter 7 in the Sullivan Pre-Cal book, Section 1 today. And so as we go on, we're going to talk about these objectives. Trying to find the exact value of an inverse sine function. Find the approximate value of an inverse sine function. Use properties of inverse functions to find exact values of composite functions. Find the inverse function of a trig function. Solve equations involving inverse trig functions. So as we move forward then, before I want to talk about this, I want to talk a little bit about what we already know about inverses. We know that inverses, if you compose an inverse with a function with its inverse, your answer is x. If you have a set of points on a function, the inverse is just to reverse the set of points. So because of that, we know that the range of the inverse is the same as the domain of the function, and the domain of the inverse is the same as the range of the function. And so sometimes if we know the domain of one, we know the range of the other, and vice versa. We know that inverse functions are symmetric about the line y equals x. And we know that if f of x, well, for a set of points, say if f of 3 equals 11 in the regular function, then f of 11 equals 3 in the inverse function. Again, that's just you swap the values of your points. Now, as we look at this and we start talking about inverse functions for trigonometric functions, we first have to notice that this is continuous. This is looking at the sine curve over its entire domain, which is from negative infinity to positive infinity. What we do notice that is that this has repeating y values. And because of that, then we can't find an inverse of anything that has repeating y values. So if we want to find the inverse of a sine function, we have to restrict the domain so that it has only one set of y values. And so in other words, we look at the blue portion of this sine curve, and that's what you'll do if you want to find an inverse of a function that where that happens. And so we're going to restrict the domain that we look for the inverse of sine of x from negative pi over 2 to pi over 2. Now that does a couple things. It makes it so all the range value, every x is unique and every y is unique. It covers the whole range of the sine function from negative 1 to 1. There's nothing left out of it. And so that's the reason we restrict the domain of the sine and cosine functions when we're finding the inverses. Okay? So we go from negative pi over 2 to pi over 2, which is quadrant 4 and quadrant 1. Is where we look for the answers when we're using inverse functions. Okay, so we've already talked about that. We've restricted our sign in the domain of negative pi over 2 to pi over 2. So the inverse sine symbol is sine with a superscript negative 1, or the inverse function symbol, it has a negative 1. It looks like an exponent, but it means inverse. So if y is the angle that has a sine of x, then x must be the sine of y. And so we need to be able to interchange these two formularies or these two methods of writing this function in order to sometimes solve or to use. We're going to need to be able to use both of these. So y is the angle that has the sine of x, and so x must be the sine of y. We're going to go, our x is from negative 1 to 1. And our y is negative pi over 2 to pi over 2. Now remember, again, when we're talking about before, the negative 1 to 1 was our range, it was our y values. and the angle was our x values. But when we're talking about inverse, we've inverted those, we've reversed those. So our range is now the angle, and our negative 1 to 1 is our x value. This shows the sine x curve and that portion of the sine curve we're using for our domain. In other words, all of them are from negative pi over 2 to pi over 2. The red value is our original function, and the blue curve is the inverse sine function. So, to get on to the meat of this, we're going to find the exact value of an inverse sine function. Now, these are our typical thetas and sine thetas for the sine curve. So remember, we reverse these when we're looking for the inverse, but we still have these same values. Okay. So I think it's easier to read this when you see sine negative 1. Read it the angle that has a sine, because you're always looking for the angle when you have the inverse. The angle that has a sine of negative 1/2. Well, if we look back at our table, negative pi over 6 has a sine of negative 1/2, which makes sense because that's a pi over 6 in the first quadrant. Remember, the first quadrant we're going to have positives. Second quadrant we're going to have negatives. And so you can see here we have our pi over 6, which has right here, I'm going to annotate this. Here we have our pi over 6 that has a half. In the first quadrant, if we go negative 1/2, or negative pi over 6, down from the x-axis, then we have a sine of negative 1/2. Okay. So the angle that has a sine of negative 1/2 has to be between negative pi over 2 and pi over 2. And that will be negative pi over 6. And that's the only angle in the interval that has that combination of sine of negative 1/2. That's in that interval. Alright, find the approximate value of an inverse sine function. Now these we'll do on a calculator. These are the ones that don't have the typical pi over 6, pi over 4, pi over 3, or quadrantal values. So you're going to do, in your calculator, express the angles in radian rounded to 2 decimal places. The sine negative 1, you do second sine. So do second sine, parentheses, 1 divided by 3, close your parentheses, and enter. For B, second sine, parentheses, negative 1 divided by 4. Since this is exact, if you want to just do negative 0.25, that would be fine. Close your parentheses, enter, and express the answer in radians rounded to 2 decimal places. So you can see this is what you're going to be sure you're in radians. That's the key. Right here, highlight. First set the mode, whoops. Put my highlighter on. First set the mode of calculated in radians. That's the most important part of this whole piece. Okay. Now your TI and Spires probably have the inverse functions on there. For the 84, you just have to hit second sine and get the inverse function. So we would round this to negative 0.25. So now the properties of inverse functions, we're going to use them to find exact values of composite functions. Remember, a composite function, when you compose a function, you put one function inside of the other function. So here's composite functions. We have the inverse f negative 1 of f of x, which is going to equal to the inverse sine composed with the sine function, and that should equal x. Okay? And again, when our domain is between negative pi over 2 and pi over 2. If I compose start with the function composed with its inverse, that equals x, And that's going to fall in the range between -1 and 1. Okay? So you just have to remember which way is which. If the inverse is listed first, you're looking in the domain of pi over 2 to pi over 2, negative pi over 2 to pi over 2. If it's the function that's listed first, you're looking in that for the -1 to 1. Okay, so find the exact value of certain composite functions. The angle, we want the angle that has a sine. Okay, the angle that has a sine of sine pi over 8. Okay, then we want the angle that has a sine of sine 5 pi over 8. Well, let's talk about the first one. Let's talk about A. So if you look at this, we're going to look at A, the solution set. The composite function, pi over 8, is in the interval between negative pi over 2 and pi over 2. So the angle that has a sine of pi over 8 is pi over 8. The angle that has the sine of pi over 8 is equal to pi over 8. Okay. Now the next one, though, let's think about that. Where is 5 pi over 8? If you look at the little graph here on the side, 5 pi over 8 is in the second quadrant. That is not in the domain that we're looking for. We're looking, remember, in the fourth and the first quadrant. So we need to think of an angle in the domain that would have the same sign as 5 pi over 8. Well, in the second quadrant, sine is positive. So in the first quadrant, that's where we'll look for a positive sign, which would be the reference angle of 3 pi over 8 would have the same sign as 5 pi over 8. Okay, now you can see from that picture, so hopefully that's clear. So we're going to look for, the angle that has the same sign as the sine of 5 pi over 8 would be 3 pi over 8 in the domain that we need it to be. Okay, so some of these, if they're not in the fourth or the first quadrant, you're going to have to figure out what angle would match it that is in the fourth or the first quadrant. Okay. Now we're going to look at cosine, and again, we still have to restrict cosine so that it is where we can cover all the range and have it just be a 1-to-1 function, 1x to 1y. Because it, like the sine function, is not normally 1-to-1. So we're going to restrict this from 0 to pi, which is in the first and second quadrant for cosine. Using just the blue part of the graph so that we cover all the range and we don't have any repeating y values. Okay. Same thing as far as this definition. If y is the angle that has a cosine of x, then x is the cosine of y. We're looking for our x's as -1 to 1 and our y's from 0 to pi. That's the only piece that's different than really what we saw in the sine function, is we're looking in a different range, or we're looking from 0 to pi instead of from -pi over 2 to pi over 2. Again, this is a graph that shows it's symmetric about the y equals x line, which indicates that it is these two are inverses of one another. The point 0, 1 is on one of them, 1, 0 on the other, -1 pi and pi -1. The points are reversed for the two graphs. So we want the exact value of the inverse cosine function. We're going to find the same exact thing. We want the angle that has a cosine of -√2/2. Okay. So we know that cosine theta must be -√2/2. So looking at table 2, for an interval between 0 and pi, For cosine to be negative, it has to be in the second quadrant, and that would be a 45-degree angle derivative, sort of, in the second quadrant, which would be 3 pi over 4. So that's the angle that would have a cosine of negative square root of 2 over 2 that is between 0 and pi. Okay, and you can see this is where it's going to show we want negative square root of 2 over 2 right here. Okay, be 3 pi over 4. Okay. Now, if we want to find composite functions, it's the same exact thing. If we have the f negative 1 on the outside, we want the angle that has a cosine. The angle that has the same cosine as cosine of x. So it's going to be x. It's going to be your angle. Again, that's the angle between 0 and pi. If the function's on the outside, we want the function that has the angle of x. We want cosine of the cosine that we want a cosine of the angle that has a cosine of x. It's going to be x, between negative 1 and 1. So let's work a couple of these problems. It says use properties of inverse functions to find the exact value of certain composite functions. Cosine, we want the angle that has a cosine, angle that has the same cosine as the cosine of pi over 12. Pi over 12 is in the first quadrant, so it should be pi over 12 should be our answer. So let's look. A is pi over 12. Okay. B, we want the cosine of, now again, this we're going to look for a number between negative 1 and 1. We want the cosine of the angle that has a cosine of negative 0.4. Okay, so if the angle has a cosine of negative 0.4, that's between negative 1 and 1, so it should be negative 0.4. And it is. Now let's look at C. We want the angle that has the same cosine as, we want the angle that has, I'm trying to think of the best way to read this. We want the angle that has a cosine of the angle that has, of cosine of negative 2 pi over 3. Is negative 2 pi over 3 between negative pi, or excuse me, between 0 and pi? Well, it is, and see, negative 2 pi over 3 is not. Negative 2 pi over 3 actually would be, we'd have to draw our, we'd go, this is negative pi over 3, this is negative 2 pi over 3. Okay, so our reference angle here is pi over 3, but it's not pi over 3 that's in the second quadrant or the first quadrant. Now, this angle here, though, is going to have, from looking at this reference angle, let me color it a little bit. If I'm looking for this reference angle right here, okay, that's going to have a negative cosine. So I'm going to have to really find this angle. This pi over 3, that's the one that's going to have a negative cosine, which if I draw it from the positive x-axis, that's going to be 2 pi over 3. Okay, that's going to get me the angle that has the same cosine as negative 2 pi over 3, but it's in the right domain. It's in the first or second quadrant. So it's going to be 2 pi over 3 should be our answer for that one. So let's look and make sure that we're right. Okay, and it is 2 pi over 3. That would be the angle that's in the interval of 0 to pi. Now let's look at D. We want the cosine. This time we have to be between negative 1 and 1. We want the cosine of the angle that has a cosine of pi. So that would mean the cosine of the angle we're looking for would be pi, and pi is 3.14. So pi is not between -1 and 1. So for this one, there would be no solution. Pi is not in the interval -1 to 1. The domain of the inverse cosine is not defined. So it's not defined. No solution. Alright, so y equals tangent of x. Now let's look at tangent of x. Again, it's not 1 to 1. There are repeating values of y, so we're going to restrict the domain. We look, in and around 0. And so this looks like we can go from -pi/2 to pi/2, just like we did with the sine function, to restrict the domain. Now there are asymptotes at -pi/2 and pi/2, so it will never actually be equal to those things, but we still say that it's in the domain of -pi/2 to pi/2, and then we just have the curved brackets because it can't include either one of those things. Okay? Again, the same way to write this. If y is the angle that has a tangent of x, then x will be the tangent of y. The range was -infinity to infinity, so now the domain is -infinity to infinity, and our range will be from -pi/2 to pi/2. Picture of it across, showing that it's a reflection across y equals x. So, find the exact value of the angle that has a tangent of 1. Well, tangent is y over x. So 1 is at a 45-degree angle, or pi/4. Okay. And it has to be, again, in the first or fourth quadrant. So it's +1, so it will be, tangent is positive in the first quadrant and the third quadrant, so it will be in the first quadrant. Okay, for our second B, we want the angle that has a tangent of -√3. Okay, so we're going to look in the interval from -pi/2 to pi/2. This one will be in the fourth quadrant. It will be -pi/3 would be the only angle. And then look at it's y over x, remember. So look for the angle that would have that tangent. And here's the table if you want the table. And you can see we would have been at negative, this one. That's what we would be looking for our last problem. Okay. Composed functions with tangent. Same thing, except now our range can be -infinity to +infinity if the function is listed first. Our answer can be any real number. So if they were looking for the tangent of the one that didn't have a solution before, we could have used it if it was a tangent function. Okay. Find the inverse function of a trig function. So finding the inverse of f of x. Now remember, the first thing we did when we found inverses way back is we swapped our x and y and we solved back for y. So it's kind of the same process, and we have to look between -pi/2 and pi/2, and then we want to find the domain and range of any of these functions. So let's look. This is a 1-to-1 function if we again restrict the domain. So we have y equals 2 sine x minus 1. So we're going to swap our x and y. X is equal to 2 sine y minus 1. Then you solve back for y, for sine of y. And then we have to apply the definition. Remember that if we have sine of y equals x plus 1 over 2, then y must be equal to the inverse sine of x plus 1 over 2. And so that would be our inverse function. And you would change, at the last step, change your y to f-1 of x. Okay, so the range, let's look at, sometimes again it's easier looking for domain and range, to think about our original function than our inverse function. Sometimes it's not. Okay, so to find the range, we're going to solve the original function for sine of x. And as we rearrange that, it'll be y plus 1 divided by 2. Okay, so sine of x has to be between negative 1 and 1. Okay, the range has to be between negative 1 and 1. Okay, so we can say that negative 1 is less than or equal to y plus 1 over 2, which is less than or equal to 1, and solve it for our range of the original function. That means that's the domain of the inverse. Okay, so the range of our original function is negative 3 is less than y, which is less than or equal to 1, or in interval notation, square bracket, negative 3 comma 1. And the range of our original the range of the domain of the original function was already restricted from negative pi over 2 to pi over 2, but just before, so we could even work with this problem. And so that's going to equal the domain. So the restrictions we arbitrarily placed on the domain of our original function become the range of the inverse function. Okay, solve equations involving inverse trig functions. So we have 3 times the inverse sine of x equals pi. So we're going to solve for the inverse sine. And then we're going to say, once we do that, we just divide both sides by 3, then we apply the definition. If y is equal to the angle that has the sine of x, x is equal to the sine of y. So if pi over 3 is equal to sine negative 1 of x, x must be the sine of pi over 3, and then you just look it up or figure it out. The solution is square root of 3 over 2. Okay. And that's the end of this particular PowerPoint. Your homework is combined with 7.2, so you probably want to watch that video as well.